Then you can also have a situation like this, which is actually semi-supervised, and this is like monocular. See, till now what I mean, I have kind of tried to put them in some sequence so that you understand. So, the first two, as I said, are kind of block matching, and therefore, it is only a part of, it is not end to end. I mean the other paper that I showed was bringing in the context, but then again, right, it is not end to end. Even third one, right, that we talked about was unsupervised, that is actually end to end, and also it is also unsupervised, but then that is for a stereo setup. Now this other paper, right, that is here, that is about monocular depth. Okay, that means you do not have really a stereo pair. So right, how do you actually do this, right? And by semi supervised, what they mean is there is a depth map that is coming from a different sensor, which is let us say a lidar. Okay, in this case, I think it's basically a 3D laser. So what this gives you a kind of a sparse sort of a depth map, right? So here is a scene for you, and then if you had a dense depth map, right, this is how ideally it should look like, but then what you have is a sparse sort of a depth map, and therefore, right, therefore it's called actually semi supervised. So the points, right, where you have a depth map, right, or the information, especially that's coming from the other sensor, there you can, that part you can use as a ground truth, and then for this rest of the portions you don't have the ground truth, right, and therefore again, right, I mean you have to do this kind of a left right consistency in order to check, right, I mean, are you able to match the images correctly or not. But yeah, but then, right, this is like I say monocular case, and then the other one, right, that I also kind of wanted to briefly touch upon is this wide context learning. So this again coming back to stereo matching, but then you see this one, right, this network that they have thrown in, right, in between, it's called a wide context learning. And what does wide context again means is that the earlier case that you saw was a multi-scale kind of a situation, right, where you were downsampling and then trying to sort of increase this receptive field. This is a direct way of increasing a receptive field. So this you must have heard about SPP, right, spatial, this one, pyramid pooling. We didn't do it, right, I mean the course, but then, right, it simply means that actually, right, it is used more for the case wherein whatever be the input size, if you want to finally reduce them to one single sort of size, right, that is where SPP comes. But in this context, right, why we think of it as a wide context, right, is like this AP is actually average pooling. And this 8 by 8, right, what this means is that you are actually dividing whatever be the feature map that's coming in, right, you are actually breaking it down into say 8 cross 8 regions, and you're trying to map, right, I mean, so you're doing average pooling on, let's say, each of those blocks. And the idea is that, right, so for example, the information, right, that is coming from this 8 by 8 is like I mean, so if you look at the averaging, right, that's going on, right, you are averaging over a much larger region. Then when you go to 64 cross 64, right, that means you are averaging over a smaller region perhaps, right. But then irrespective of what the feature map is having, but the point is that in one case, right, you get to do this average pooling over a larger region. In another case, you get to do this average pooling over a small region, and the idea is that the context, right, is what is then entering, okay, into the picture. And there is still no clear insights into, right, how this helps, for example, how this helps you counter noise, how this helps you counter illumination and all, right, because that kind of an explainability is still lacking. Okay, people have been only able to show results, right, so it's like intuitive, right, you kind of which is also the reason why the other way to do it is using a dilated convolution. They use both, right, you guys know about this is a dilated convolution, right. Dilated simply means that, right, you instead of a normal convolution, right, I mean, see, for example, I mean, if I did a normal convolution, what I would do, let's say it's a 3 cross 3, then I will kind of, so if this is my input image, right, I'll just look at these locations, and then this, right, I just whatever is that value, I copy here. Now in a kind of a dilated convolution, right, you tell the kind of a dilation rate. So for example, right, but if you have a certain rate, then what could happen is, then instead of sampling this image like this, right, you would actually sample it, on a kind of, so you'll still have a 3 cross 3 kernel only, but then right, the it's kind of spread out, right. So you have, so instead of sampling these adjacent locations, you are sampling with some gaps in between, right. It's also called the at-rest convolution. I'm sure, right, many of you have probably read it somewhere. So these are all different types of convolutions, and one of them is this also called dilated, or I think the other word used for that is at-rest convolution. And this actually helps you kind of get a kind of larger field, I mean, without without actually involving more unknowns, right. There is still 3 cross 3 only. I still have those 9 parameters. Imagine, I mean, if I wanted a 5 cross 5, right, then I would have had to have one 3 cross 3 followed by like one more get a 3 cross 3 if I was doing a regular convolution, right. That's how I will get a 5 cross 5 receptive field. Now, in this case, right, of course, you are sacrificing a little bit. I mean, in the sense that, right, I mean, in between, right, you are not caring about it, but that's the way it is, right. Address convolution works that way, right, and these guys have tried to incorporate wide context, right. So, this context business and wide context, right, it's coming through the spatial pyramid pooling, and this is a dilated convolution. Yeah, then the left right consistency, right, I have already talked about, but then, right, the only sort of a difference in this paper is, right, they use one of the images, that is, let us say, the left image, do a prediction of both the left disparity as well as the right disparity, and then what they will do is they will take the left image, use the right left sort of use the right image, use the left disparity, produce an estimate of IL. Then they will use the left image, use the right disparity along with it to actually produce IR hat, and they will compare IR and IL, because IR and IL, you know how they are, right. So, this left right consistency is like over both left and right. I mean, you warp once through a right disparity map, once through a left disparity map. So, IL will be acted upon by DR, IR will be acted upon DL, and if you act it upon, then you should actually get back your original pair, because that is all that you have. So, again, right, this is unsupervised, right, and this is another way to do, and then this is actually deep MVS. Okay, so this is like the multi-view stereo thing, right, that we did, and this actually goes back and uses all that plane sweep stereo and all, right. So, the idea is like this. So here, right, if you look at this plane sweep volume, right, this is like saying that for you see one depth, right, you will get kind of one volume. For another depth, right, you will get another volume. For another depth, right, you will get one volume. So, depth or kind of a disparity. So, I think they use like 100 of them, right, 0th kind of a disparity, then 99th disparity. So, it means they have sliced the 3D scene into 100 planes. So, what I am trying to say is, right, many of these methods do go back and use the things, right, that are actually classical in nature, but how they kind of put that in and in what form they use it, how they use it is what kind of, right, differs from one paper to another. So, this plane sweep volume, right, we know, right, what it actually means, and then what they do is they have a kind of, right, a photo consistency, right, sort of a network. What this actually does is that right. So, it actually creates a 400 channel sort of an output, and then, right, this is then passed through this unit, right, and this unit also gets the semantic information. That's why, right, I mean, so this context, right, that we are talking about here, the context is coming through a different way in which it's coming through a VGG net, right, and that input is also sent to this unit along with this kind of with this feature volume, right, that you have, and out comes a kind of 800 feature layer, and this right, and this they do for every this one a reference view. So, if you look at this, right, if you actually notice, right, for one volume, right, you get actually a 4 channel output, right, and then you have 100 of them, okay, which is the reason why you have this 400, right, and then right, then this 400 goes into this network, and then out comes an 800 channel layer, and this they still call this intra volume feature aggregation, right, because everything is happening with respect to one reference frame, and then everything else is being warped at, let us say, various depth planes. Then they use what is called intervolume. So, what this intervolume means is that now you change, instead of using, let us say, the first reference image, now you use a second as a reference, now you do right, repeat the entire operation, then you get another sort of an 800 feature vector, then you kind of right, do it for the next image. So, this input is like as many views as you have, right. I mean, here right, it's like as many disparity levels as you have. Here it's like as many views as you have, and all those are sent into some max pooling. Again, right, that's why it's called intervolume feature aggregation, and then it is supervised, by the way, right. It is not unsupervised. So, the output you predict a disparity map. So, for example, right, I mean, so you have 100 values, right. So, it's like a 100 valued sort of a disparity map, and you again compare it with actually with a ground truth, and the ground truth here I believe is synthesized, right. So, it's called MBS synth. So, this is actually a completely synthetic data set, but they claim that they have been able to introduce lots of things into it, like color changes, whatever I said, right, illumination, all of that is sitting there, and then they say that, right, once you train this network on this what is this multi-view stereo synth data set, right. Then they show that right, you can take it to a different data set, and you can see, right, for example, if you see this building, right, and right, I mean, outcomes a 3D structure like that. Then from here to here, right, you can still see this kind of building, right, coming up in the front and whatever, right. And they also compare with what is called a coal map as a standard kind of structure from motion, kind of a traditional method. So they compare it and they show that probably, right, with deep MBS, right, you've got much less noise and it's far more accurate and so on, right. Then the last one, right, that what I wanted to talk about was structure from motion. All the earlier ones were all on stereo. That you can also ask about is structure from motion, right. So what if you had a monocular video. So here the idea is that, right, you have lots of unlabeled video clips, right. What that means is that, I mean, you don't know the kind of structure or anything. You just have several video clips taken from a camera, and what you do is, you actually build two of these networks, right. One is called a depth CNN, another is actually called a post CNN. So the idea is that how do you do unsupervised learning of depth and ego motion. By the way, right, this word ego motion, I should have used it. I think I never used this ego motion. So ego motion means the camera motion. Okay, that's what basically, right, ego motion means. And the idea is that, right, just like we do, right, in structure from motion, what would we have done, right? We would have said, calculate for me all the camera poses as well as the structure of the scene. That's what we do in SFM. Right? That's exactly what is being asked here. What is the ego motion and what is the depth? And the way it works is as follows, right. So you have sort of a reference view that you can pick, and you actually build a depth CNN, and this is completely unsupervised. Okay, so what you do is you kind of have a depth CNN. Let's say, right, initially it is supposed to give out a depth map. Initially, of course, right, it will not be able to do it. It will give you something, right, and that is your D, right. That is sort of a depth map that you have with you. Then what you do is you give your nearby views. Now, if I remember right, what they do is they actually train with 3 frames. That means you have like a reference frame which is TT. They have TT minus 1. Then they have TT plus 1. Okay, and they kind of they ask for the post between this and this, and kind of this and this. That's called a post network. So this post network is supposed to give you, let's say, R1 T1, and then it's supposed to give you R2, C T2. Okay, and then the idea is that, right, you go back and do the, see, now this is not like left right consistency, right. This is not like stereo match. So you don't call it a left right consistency. What you do is you still have to look for this is called view consistency. Okay, the difference between the earlier ones where we did stereo, we kept on saying left right, but this is not left right, because this is like a view. So I have one view from here, I have another view from here, I'm moving, and then I'm getting different views, and I'm looking for view consistency. And the view consistency, right, if you go back, what was that equation, man, I don't exactly remember, maybe you can remind. What was that, x tilde dash, right? We had, when I was talking about view synthesis, you guys remember, it was some k inverse, and I think there was some RT which was the pose. And then you have a vector, right, Z, and then you had another k inverse. I don't know which one was KL and which one was KR. I think this was KR, KL, and this was KR. Sorry. And then you had a Z KR inverse, and then you had an x tilde, and then 1. It's something like this we had, right? If you guys going to say, if you guys recollect. Okay, this is what I had said people use for actually view synthesis, right? And this is exactly the equation that goes in here. Because the view synthesis, you can't just do it in air, right? I mean, you have to do some kind of a view. Therefore, you have the R and T, right? And then Z is from here. So you have a depth net which gives you the Z. You have the R and T which comes from the post net, and the intrinsic, right, is supposed to be known. And typically, you don't have KL and KR. This is the same camera. It's just 1K, right? And the idea is that, right, you do this view synthesis, and what is the view that you have? You already have these views with you, right? So what do you do when you kind of take this TT, which is a reference view, you warp it. You warp it so as to match your TT minus 1 view and TT plus 1 view using this D and this Z. This D and this R and T, the post net. And right, if there is an error, then you sort of go back, right? Then you kind of keep training this network, and you can show it, right, tons and tons of video clips. The nice thing about this network is you don't need anything, right? You just have to have this right, videos taken, right? Tons of them. Keep on giving them, and ask for a view consistency check, which simply means that, right, it needs to keep on synthesizing the views, and then at the end of it, right, it's completely trained. Now this network, you can actually use it in several ways, right? Sometimes you can throw away all of this, right? You may not even need this, and I can simply use this depth CNN. What that means is a monocular depth. That means I just give you give this network an image, and then it knows to try to give me a depth map for that, right. I mean, I don't need anything else. I can just give it a single after training, right. After training, I can either use this whole thing as it is. That means that I can give frames like 3 frames, and then at one target view, and then at the output it will give me a depth map corresponding to the target view, and then it will give me R and T, which are the other poses if I need them. Other way to use it is throw away everything, use simply a depth CNN, wherein any image that you input, because this depth CNN has figured out how to kind of compute a depth map given, because it only sees that image, right, the input image, and therefore it can actually give you a depth map. You can also use the postnet separately if you wish. That means that if I have 3 frames and I want to know what is the relation between them, right, it can because it just needs those frames. You can train it with as many frames as you want, right, depends upon how you have trained it. If you have trained it with 3 frames, then for those 3 frames it will give the mutual poses. This can all be useful depending upon what kind of a problem you are dealing with. For example, if you are doing some kind of a video super resolution and so on, and if you want to know R and T and you are not interested in other things, then you can probably use the postnet alone. So, all of that, right, is entirely sort of out in the open, right, how you want to do that, and this was actually a 2017 paper, right. So, anyway, I mean, there are say tons and tons of papers. The idea is not to go through all of them, but to sort of give you a rough sketch about what these deep networks kind of do, and you should be able to read them up, right. Now that you have enough background, you can just go read them up and you will be able to understand what they are doing and why they are doing. There are a few other things like this cost volume and cost aggregation and all, right, which I have not talked about within these networks. That, I mean, you will have to read the papers. I mean, there is more kind of detail right out there. But yeah, if you feel that certain things you want to understand better, I have given you the paper titles, just go there and read them up.